Ayubowan students, and a very warm welcome to Study Hub Sri Lanka. Today we're going to tackle a really important chapter from your grade 13 physics syllabus, viscosity. Now, I know it might sound a little complicated, but trust me, by the end of this session, you're going to have a really clear understanding of it.
Okay, so let's start with something you see every day. Have you ever wondered why, when you pour coconut oil or maybe some honey, it flows so slowly? But then you pour water and it just gushes out. You see it all the time in the kitchen, right? Well, that's not just random, it's physics. And that specific property that causes this difference, that's exactly what we're here to talk about. It's called viscosity.
So here's our game plan for today. First, we'll get down to the basics. What exactly is viscosity? Then we'll look at the different ways fluids can flow. After that, we'll jump into the numbers and see how we can measure viscosity. And then we'll flip the idea around and see what happens when things fall through fluids. To finish it all off, we'll solve a proper problem using Stokes' law. You know, just like you might see in your A-level exam. All right, let's get started.
Right. First things first, we need a proper scientific definition for this property that makes honey thick and water thin. Let's really pin down what it means for a liquid to be viscous.
Okay, so here it is. Viscosity is, quite simply, a measure of a fluid's internal friction. That's the key phrase right there, internal friction. It's like the liquid is rubbing against itself. This friction does two things. It pushes back against anything trying to move through it, and it also creates friction between the different layers of the liquid itself as they try to slide past each other. Just remember that term, internal friction. Now, before we can even think about measuring this friction, you need to understand something very important. Not all flow is the same. The way a liquid moves is critical, and for your A-levels, there are two main types you absolutely need to know. And this picture shows the two types perfectly. On the left side, you've got what we call turbulent flow. Look at it. It's chaotic, disorderly, full of eddies and swirls. Think of a fast, rough river. Now look to the right. That is streamline flow, or sometimes we call it laminar flow. See how smooth and orderly it is? The liquid is moving in nice, neat, parallel layers. It's this smooth, streamlined flow that we're interested in for our calculations. Okay, so now that we have this picture of orderly, layered flow in our heads, we can start to figure out how to measure that frictional force between the layers. It's time to put a number on this stickiness or thickness of a liquid. Let's build up the equation. This diagram is a great way to visualize what's happening. Just imagine two layers of liquid, one right on top of the other. They have a certain area of contact, which we'll call A. Now the top layer is moving a little faster than the bottom one. That viscous force, F, is the drag, that friction, between these two layers that's trying to slow the top one down. So what determines how strong this force is? Well, it's proportional to two key things. First, the area A of the layers. That makes sense, right? A bigger area of contact means more friction. And second, something called the velocity gradient. It sounds complicated, but it's just the change in velocity divided by the distance between the layers. Basically, it tells you how much the speed changes as you go from one layer to the next. A really sharp change means a big velocity gradient and a big force. And when we combine those two ideas, we get this, Newton's equation of viscosity. The force F is equal to some constant times the area A times that velocity gradient. That Greek symbol there, the one that looks like an N with a long tail, that's eta. And eta is our constant of proportionality. We call it the coefficient of viscosity. It's the actual number that tells you how viscous a liquid is. A big eta means a very viscous liquid, like hi. Now, Newton's equation is perfect for looking at the force between layers. But what if we want to know about the total amount of liquid flowing through a whole pipe, like a very thin tube? For that specific job, we have another formula, Poiseuille's equation. This one helps us find the rate of flow, but it only works if certain conditions are met. And these are the conditions you have to remember for your exams, okay? The flow has to be streamlined, not turbulent. The fluid needs to be incompressible, meaning its density stays the same. The flow must be steady, not speeding up or slowing down. And the tube has to be horizontal and narrow. If all those are true, Poiseuille's equation is your tool. All right. All right, so we've been talking a lot about fluids flowing in pipes. Let's switch our thinking.
what happens when the fluid is still and an object, let's say a small ball bearing, is falling through it? The physics is a little different, but it's all connected. Take a look at this graph. When the ball is first dropped, it accelerates, right? Gravity is pulling it down. But as its speed increases, that viscous drag force pushing up gets stronger and stronger. Eventually, you reach a point where the upward forces, that's the viscous drag plus the upthrust from the liquid, perfectly balance the downward force of the ball's weight. At that exact moment, the net force becomes zero, the acceleration stops, and the ball continues to fall at a constant maximum speed. We have a special name for this: terminal velocity. So, how can we calculate that viscous drag force on the sphere once it reaches terminal velocity? For this, we use a very famous formula called Stokes' law. Let's just break it down. The viscous force F equals 6 times pi times eta, our old friend, the coefficient of viscosity, times a, which is the radius of the sphere, and finally times v, the terminal velocity. And just like with Poiseuille's equation, Stokes' law works best under a set of ideal conditions. The fluid shouldn't be moving, it should be really large compared to the sphere. We say infinite in extent, which just means the walls of the container aren't close enough to interfere, and the sphere itself should be perfectly smooth and rigid and dropped from a standstill. For your exam problems, we usually just assume all these conditions are met. Right, that's enough theory for now. The absolute best way to really understand all this is to use it. So let's work through an example together, just like one you might face in your final physics paper. Okay, here's the problem. We have a small steel ball and it's falling through some oil at a uniform velocity. That's a T-phrase. That's a T-phrase. We're given its diameter, how far it fell, and how long it took. The mission is to figure out the viscosity of the oil. So, what's the first step in any physics problem? We list down everything we know. The diameter is 8 millimeters, so the radius, A, is 4 millimeters, or 4 times 10 to the minus 3 meters. The velocity, V, is just distance over time. And we're given the densities of both the steel and the oil. Perfect. We have all our data ready. Now, this diagram shows the single most important idea for solving this. Remember the question said uniform velocity? That's our clue. It means terminal velocity. It means the forces are perfectly balanced. The downward force, the ball's weight W, must be exactly equal to the two upward forces added together, the upthrust U plus the viscous force F. So we just work through it step by step. First, we calculate the weight of the steel ball. That comes out to 0.02 newtons. Next, we calculate the upthrust, which is just the weight of the oil that the ball pushes out of the way. That's a much smaller number, about 0.00241 newtons. Now, since W equals U plus F, we can just rearrange it to find F. The viscous force is the weight minus the upthrust, which gives us 0.01759 newtons. We're almost there. And for the final step, we bring in Stokes' law. We know F equals 6 pi eta AV. We want to find eta, so we rearrange the equation. Eta equals F divided by 6 pi AV. Now we just have to plug in all the numbers we already found, the force F, the radius A, and the velocity V. You do the calculation, and you get our final answer. The coefficient of viscosity for this oil is 0.65 newton seconds per square meter. Meter. So let's do a very quick review of the most important points. Number 1, viscosity is just internal friction. Number 2, flow can be smooth and orderly, which is streamline, or messy and chaotic, which is turbulent. Number 3, we have two powerful tools to calculate forces, Newton's equation and Stokes' law. And finally, the whole idea of terminal velocity boils down to one simple thing. All the forces are balanced and the net force is zero. Okay, before we finish, here's a little something for you to think about. In a car engine, the motor oil is designed so its viscosity gets lower as the engine heats up. Why do you think that is so important for the engine to work properly? Think about what the oil needs to do when you first start the car on a cold morning versus when the engine is running hot on the highway. It's a fantastic real-world example of everything we just learned. Thank you for joining me for this lesson today. I really hope you found it helpful.
And please, before you go, don't forget to subscribe to our channel, Study Hub Sri Lanka, and make sure you click that little bell icon. If you do that, you'll get an update immediately whenever we post a new lesson for you. Keep up the great work with your studies, and I'll see you in the next one.